Welcome to qnawire.
We begin this question by calculating the acceleration of the duck. For that, we have to use Newton's second law, and I'm using the following reference frame. This is my y-axis and this is my x-axis. Then, Newton's second law tells us that in the x direction, the net force is equals to the mass of the duck times its acceleration in the x direction. The net force that acts on the duck in the x direction is composed by two forces, F1, which points to the positive direction, and the x component of F2, which also points to the positive x direction. And this is equals to the mass of the duck times its acceleration. To calculate the x component of the force F2, we have to decompose it as follows. It has a y component, which points in this direction, and then its x component. This is F2 component y, and this is F2 component x. As you can see, this angle is 90 degrees. If this is 52 degrees, then this other angle here must be an angle of 90 minus 52. And 90 minus 52 is 38 degrees. And then, using this triangle, we can get a relation between the magnitude of F2 and its x component. So, using the sine, we get the following. The sine of 38 degrees is equal to the opposite side, F2 component x, divided by the hypotenuse, F2. Then, F2 component x is given by F2 times the sine of 38. Then, using that result in the expression for the second law that we have, we get that the acceleration in the x direction is given by F1 plus F2 times the sine of 38 degrees divided by the mass of the duck. Then, plugging in the values that the problem gives us, we get AX being equals to 0.1 plus 0.2 times the sine of 38 degrees divided by the mass of 2.5 kilograms. This results in an x acceleration of approximately 0.08925 meters per second squared. And now that we have the x acceleration, we proceed to calculate the y acceleration. For that, I have to organize my board. So give me a second. Okay, so for the y component, Newton's second law tells us that the net force is given by the mass times the y acceleration. In the y direction, there is only one force acting, which is the y component of the force F2. Then we have minus F2 component y, minus because F2 component y points to the negative y direction, is equals to the mass of the duck times its y acceleration. Then the duck's y acceleration is minus F2 component y divided by the mass. Now looking at this triangle again, we can use now the cosine of 38 to get a relation between F2 component y and F2. So the cosine of 38 degrees is given by the adjacent side, F2 component y, divided by the magnitude F2, which is equivalent to the hypotenuse of the triangle. Then F2 component y is equals to F2 times the cosine of 38 degrees. So the y acceleration is minus F2 times the cosine of 38 degrees divided by the mass of the duck. Then plugging in the values that the problem gives us, we have minus 0.2 times the cosine of 38 degrees divided by 2.5, and this results in an acceleration of approximately minus 0.06304 meters per second squared. And now that we have both accelerations, we can calculate the displacement of the duck. For that, let me organize my board. Okay, so the x displacement of the duck is given by the following equation. The displacement is equals to the initial velocity times the interval of time plus the acceleration in the x direction times the interval of time squared divided by 2. Then its x displacement is given by 0.11 because the velocity points to the x direction times 3 seconds plus 0.08925 times 3 squared divided by 2. This results in a displacement that is equals to 0.7316 meters in the x direction. For the y direction, we have the y displacement is given by its initial velocity in the y direction times the interval of time plus its y acceleration times the interval of time squared divided by 2. Its initial velocity in the y direction is equals to 0 because it's not moving in that direction at all. V points to the right only. Then its y displacement is given by minus 0.06304 times 3 squared divided by 2. And this results in a displacement of approximately minus 0.2837 meters in the y direction. Then we can calculate its total displacement using a triangle. So it had a displacement in the x direction, and it also has a displacement in the y direction. They make a 90-degree angle. This is the y displacement, this is the x displacement, and this is the net displacement. Then, using the Pythagorean theorem, we can calculate the net displacement as the square root of the y displacement squared plus the x displacement squared. And this gives the square root of 0.7316 squared plus 0.2837 squared. The minus sign squared is just a plus sign. And this results in a net displacement of approximately 0.78 meters. And then for the direction of the displacement, we can do the following. Let us say that this angle is theta. Then the tangent of theta is given by the opposite side divided by the adjacent side. Therefore, theta is the inverse tangent of 0.7316 divided by 0.2837. Notice that I'm not including the minus sign because in this situation it's just one of the sides of a triangle, and the side of a triangle is always positive. Then we conclude that theta is approximately 68.8 degrees. So this is the east direction. Now we can calculate this angle that the displacement makes with the east direction. Let me call it alpha. So we know that alpha plus theta should be 90 degrees, but theta is 68.8. Then the angle between the displacement and the east direction, alpha, is given by 90 minus 68.8 degrees. And this results in an angle of approximately 21 degrees. Then the direction of displacement is 21 degrees south of east. And this is the answer to this question.